It's my pleasure to introduce Evangelos Sfakianakis. Evangelos got his PhD from MIT in 2014. This was followed by postdoc positions in Urbana-Champaign, Leiden, and Barcelona, and he is now an assistant professor at Case Western Reserve University. He'll be telling us today about the CMB signatures of standard model Higgs effects during reheating. Please take it away.
Thank you very much. Thanks for the chance to give a talk virtually. So right, this is I'm gonna talk about some work that I did with Katie Fries and her group a couple of years back, and some sort of follow-ups that we have in mind. Oh, sorry, wait, somehow the slides. Okay. So this is a sort of brief history of the universe, very brief history of the universe, actually. So most of our information about the early universe comes from the CMB, right? Although, of course, newer tools like gravitational waves allow us to go even further back in some sense to the age where the universe was not transparent to electromagnetic radiation. So one of the big pillars of the universe, or of the information comes from CMB, and I would say one more very important era for the early universe is BBNs, Big Bang nucleosynthesis. And unfortunately, we don't know much about what happened before. So in a sense, we know, or we assume we have very good evidence to support that inflation happened. But what happened at the end of inflation and until Big Bang nucleosynthesis, these are really the dark ages of the universe, where we have little to no information about what happens. And it's important because it's necessary, right? And it's hidden from us. So it's very important to understand the dynamics of what happened there. And also, we have no idea about how the Sun model evolved, right, before BBN. What other extra degrees of freedom there might have been active, and so on. So a very simple sort of mandatory slide for why inflation is cool. So inflation is a very compact, economical way to explain the early universe. Right, so it was proposed. I mean, let's say the spark that started was the monopole problem, right? But it solves the horizon flatness and monopole problems of the old Big Bang theory. And in some sense, that's why in this plot I put the Big Bang after inflation, right? Because the Big Bang as the hot expanding plasma happens after inflation, not before. But it's not just that it solves the problems; it gives us a framework to do computations, right? So when I say explains the fluctuations that we see in the CMB, it actually allows us to compute the fluctuations that we see in the CMB and go and measure them, right? And compare our theory with our observations. Now, generically, inflation predicts a nearly scale invariant spectrum, right? And the amplitude is tunable based on the model, and also the perturbations are largely Gaussian. And usually, whatever you say about inflation, there's a huge but, which is we can have this other model that can, produce non-Gaussianities or can produce a spectrum that, has a feature or whatever. But these are sort of the generic predictions of inflation if you don't put too much work into breaking them. And of course, these are the Planck data, right? And then the best fit inflationary result. And they match fantastically well with, of course, the weirdness, let's say, at low angular scales, the Lowell anomaly or whatever you want to call it, which is also problematic due to cosmic variance because the error bars there get bigger. Okay, so this is again. I'm gonna. There are two sort of schools of thought in inflation. One is okay. What's the most complicated model I can make? And maybe embedded in string theory or something like that. And the other one that I'm going to take today is, okay, I want the bare basic minimum model of inflation, right? I will not do a lot of inflation model building today, but I'm going to ask what phenomenology do I get with minimal ingredients, right? So this is sort of the minimalist approach in a sense in inflation. So the anatomy of single field inflation, you have very, very basic components. You have some flat plateau, all right, where the inflaton is rolling during slow roll. And at some point, slow roll conditions get violated. and the inflaton starts oscillating happily in its potential, let's say a quadratic or something like that. Now, of course, the inflaton must somehow transfer its energy from the inflaton must dump its energy into other degrees of freedom, because we are not made of inflatons, right? We are made of electrons and quarks and standard model stuff. So somehow during this oscillating phase, the inflaton must transfer its energy into other particles, right? This is called reheating. And one very, again, phenomenological way of doing it is if the inflaton couples, let's say, to fermion pairs, so fermion antifermion, then you can think of the inflaton as a particle, as a heavy particle, just happily sitting in the bottom of its potential and decaying with some decay rate to other particles. Okay, however, during inflation, the inflaton is not the only field that exists. Right? Every other field we know exists during inflation, and the question is, okay, what does it do? The first assumption that we have is that it does not dominate the energy density of the universe, right? So the universe is still dominated by the inflaton, but any other scalar field during inflation will be what's called a spectator field. So even if it's not directly coupled to the inflaton, it does feel the expansion of space-time, right? So we do have essentially fields on an approximately de Sitter space-time. Again, we go back to the seminal work by Starobinsky and Yokoyama, who analyzed the fluctuations of a quartic, so a scalar field with a quartic coupling in a de Sitter space-time, in a de Sitter background. And of course, there is a field we know that has a quartic potential, which is the Higgs. So if we take just the quartic, just as a sort of way of understanding what's going on, if we take the Higgs or any other quartic self-coupled, quartically self-coupled field on an expanding universe, we have this sort of mass term, this lambda h cubed. So we can see that if h is small, right, if you're at the bottom of the potential, then essentially you're massless. So the zero fluctuations want to push you up. And when you go too high up, then you start having an effective mass, right, that goes like lambda h squared, which at some point becomes bigger than the Hubble scale. So that mass wants to put you down. So there's this competition between the zero fluctuations wanting to push you up the potential and your effective mass wanting to push you down. And at some point, the field reaches an equilibrium. This is what was calculated in this paper. And this is the equilibrium probability density function of a quartic scalar field on a de Sitter background. And again, we assume the background is exactly de Sitter. Of course, inflation is not exactly de Sitter, but that is not sort of that important for the discussion. Okay, so what happens during inflation? So during inflation, as every fluctuation, as fluctuations exit the horizon, right, during inflation, you can think of the Higgs at super horizon scales getting random kicks from the fluctuation that just exited the horizon, right? So on super horizon scales, the Higgs field performs a random walk, right? And at the end of inflation, what happens, is that in each Hubble patch, the Higgs will have a different VEV, right, a different value. And you can see here, right, that initially all these patches are inside the horizon, but as they exit the horizon, they acquire sort of different values. So the blue patch will have one Higgs value, the green patch will have another, the pink, red patch another, and so on, drawn from this distribution. So now, if I go back to the sort of the toy model or simplified picture of inflation, I have my inflaton happily rolling in its potential, and then it's oscillating and it's talking to standard model fermions, right? But the standard model fermions have different masses in different parts of the universe, because the Higgs has a different VEV, meaning all the standard model particles have different masses in different Hubble patches at the end of inflation. So this is a very generic realization of an idea proposed already in 2003 and 4 by Valley, Gruzinov, and Zaldariaga, called modulated reheating, right? So in the modulated reheating scenario, what they did was they assumed there's an extrascalar field, right, which tunes, let's say, the decay width of the inflaton to other particles, and they used, for example, a linear or quadratic, so a very simple relation between that field and the decay rate. But the Higgs does it for us for free, right? The Higgs is there, and it modulates the decay rate by essentially modulating or affecting or defining the particle masses. So consider decays to fermions, as I said. So phi goes to ff tilde or ff bar. Phi is the inflaton. The first thing we can see immediately is that this decay can actually even be blocked, right? So if the mass of the inflaton is smaller than twice the mass of the fermions, right, then the inflaton cannot decay. So essentially, if we have a large VEV for the Higgs field and consider large Yukawa masses, large Yukawa couplings, then reheating can be blocked until the inflaton, until the Higgs relaxes to its minimum, right, to its true minimum after a few e-folds, when decays can resume. Now, however, in order to do this, we actually need large Yukawa couplings, so or larger than we have in the standard model, which means that Higgs blocking, while it is a possibility, it's not something that generically occurs for standard model fermions, unless somehow the Higgs is tuned to be very, very large, right? Unless there's a mechanism that goes beyond the simple quantum fluctuations that I described, or there's some way that the Higgs self-coupling is parametrically small during inflation. So you're going to need some other exotic mechanism to make Higgs blocking be really efficient. Okay, now let me take a step back and say, okay, if we don't have Higgs blocking, right, what's the point of doing this? So let's make a small sort of deviation from that, and let's say, okay, what sort of models of inflation are there sort of in reality, right? So we know that the tensor modes grow like h squared, right? This is the gravitational waves, and the scalar mode, which are the fluctuations on the CMB and in large scale structure, go like h to the 4 over phi dot squared. And this gives us one of the two sort of important data points that we get from inflation, which is the tensor scalar ratio. Right. So for R being 0.01, which is sort of roughly where our limits are right now, and where we hope to see something maybe with the next decade of CMB experiments. And this is a typo, this would be the life bound with a Y. So if we take R to be right at the edge of where we expect it to be now, or where we haven't seen it now, and taking the life bound, which relates the excursion of the field during inflation, the number of V-folds, and R, which is the tensor scalar ratio, we see that if R is large, we expect the field during inflation to have a super Planckian excursion. However, super Planckian field with super Planckian excursions suffer from quantum effect, right? From UV sensitivity effects, because if we think that the EFT of inflation has some potential that we control, plus a tower of Planck suppressed operators, then if the field is Planckian, all these Planck suppressed operators will start being relevant, which means we lose control over the potential, and it's very hard to tune all of them to give us nice low roll inflation. This is called the eta problem. So one way out of the eta problem is if we impose a shift symmetry to the inflaton, right? So if we take the inflaton as an axion, which means it can only derivatively couple. So first of all, this protects the potential from higher order terms, but it also, as a model builder, it gives me a very nice property that I cannot write down any coupling I want of the inflaton to anything else, right? So for example, I can write down derivative couplings. And one derivative I can never have derivative couplings to gauge fields and to fermions. So let me look at this so-called Chern-Simons coupling of phi to FF dual or FF tilde, right? This is a very important a very broadly studied let's say, model or coupling for the inflaton to other fields, because it can have very important phenomenology. After inflation, it can turn to, it can lead to exponential enhancement of gauge fields, magnetogenesis. Recently, there was a very nice paper about strong back reaction regime of this during inflation, where you get bursts of particle production during inflation. So this is in general a very sort of let's say actively studied topic. But here I'm gonna say something. I'm gonna take a different sort of approach to this. I'm gonna say, what if this field, this F, is actually the standard model gauge bosons, right? So the W and Z bosons. So again, the W and Z. So the moment that the Higgs acquires a VEV, electroweak symmetry is broken, right? So the W's and Z's are massive. So if my inflaton tries to decay to W bosons and Z bosons, right, it will feel that those things have a mass. I'm ignoring decays to the photon. So because I don't want to deal with the SU2, which is complicated, I write down sort of an abelian Higgs version, right? So a U1 field with a mass, and this mass is related to the VEV of the Higgs field. So they linearize the equations of motion for these A's, right? For the two polarizations, plus and minus of the mode of this gauge field. Is the following: is this, so A double dot, H A dot, and then I have this effective mass which has two components, right? One is this tachyonic amplification coming from the Chern-Simons coupling, and the other one is the mass. So you can see that K over A squared is positive. This thing can be negative, right? So it wants to create a tachyonic instability, and M squared is positive, wanting to oppose this tachyonic instability. So essentially, this M is trying to ruin what I told you here about this exponential particle production at the end of inflation. So if I look at this plot, right, on the vertical axis, I have the mass of the gauge field as a function of the Hubble scale, and on the horizontal axis, I have the coupling of the axion inflaton of my inflaton to gauge fields. Oh, sorry. And what we see is that in this gray area, we do not get efficient parametric resonance, so we do not get efficient preheating. Whereas in this sort of rainbow part of the plot, parametric resonance is active, and you can get preheating, but you can get preheating with very different, with different n, so with different duration of preheating, right? Which means that in the case of the inflaton decaying into standard model Higgs gauge bosons, right? So W's and Z's. Actually, the Higgs blocking can have a tremendous effect because it can push you from efficient preheating to no preheating at all, and everything in between. So essentially, for gauge bosons, Higgs blocking can be quite dramatic, and I'll return to that sort of later in the talk. But let's go back to the sort of more mundane thing, or more mundane or more simple decay channel of the inflaton decaying into two normal standard model fermions. Let's revisit that a bit. So the decay rate of the inflaton to fermions, I can write it in sort of having three components and three different regions. So the green sort of component is a heaviside function that tells me that when the fermions are heavier than the inflaton, I cannot decay, right? So this is the Higgs block, this part, right? So here I have the Higgs starting large and then decaying and oscillating, and here's the gamma, right? The decay rate. So the decay rate is 0 until this channel opens. When this channel opens, I don't immediately go to 1, right? I don't immediately go to sort of the nominal decay rate, because I have this just kinematic factor, right? I decay to two massive particles, so I have a kinematic factor telling me what phase space I have available for what is available for me to decay, and that defines or changes the decay rate from the decay rate I would have if I was decaying to massless fermions. And then once the Higgs completely decays, I actually asymptote to the nominal or the maximum decay rate. Now, even if no blocking occurs, this shows us, even if no blocking occurs, so here I have 3 examples. I choose 3 different Yukawa couplings and Higgs values. So this is the E-folding number starting measuring from the end of inflation onwards. And I see that even if this green region is absent, right, even if I have no Higgs blocking, actually the evolution of the decay rate of my inflaton to fermions does depend on the Yukawa and on the Higgs evolution, even if the Higgs blocking is absent. And the important thing now is not that I have a time-dependent, a time-evolving, let's say, decay rate, but that this is also space-dependent. Because as I said, in each patch of the universe, the Higgs will have a different value. So in one patch of the universe, the evolution of the decay rate will be the blue, in another one the red, in another one the green. So let's see sort of what this means. This is sort of the usual diagram for inflation, right? We start with a small patch of the universe that is in causal contact. We exponentially or exponentially expand this. Then we have the end of inflation, and then normal expansion of the universe takes over, and we live here and look back. So when we look back, right, towards two angles or two distances, two points on the CMB, what we actually see are 2 different Hubble patches at the end of inflation. So in one Hubble patch, the Higgs has a value H1, the fermions have a mass M1, right? The decay rate has a value gamma 1 or an evolution gamma 1, and then the reheating temperature will be T1. And then in another patch of the universe, we'll have Hn, Mn, gamma n, Tn. This means that there'll be a delta gamma, right? A difference in the decay rate between the 2 patches, which will result into a difference of the temperature of the 2 patches. Because if the decay rate is larger, the inflaton decays quicker, easier, larger reheat temperature. If the decay rate is smaller, the universe has more time to cool by the time it decays, so the reheat temperature is suppressed. So this allows us to actually analyze the problem. And if we write down H1, H2, H3, so we write down, we draw the value of the Higgs at each of the patches drawn from the distribution by Sorobinsky. Then we evolve the universe in each of these Hubble patches, right? We evolve the energy density of the inflaton and of radiation, so the decay product. We evolve the Higgs, and we do the self-consistent expansion dynamics, because the expansion is different if you have dominated by radiation or dominated by matter. And that allows us to look at how the initial Higgs density function, the probability density function, or the Higgs distribution evolves with time. Right? And here we see exactly that. I start with some distribution of Higgs values, and as time progresses, right, this distribution changes. And this also tells me, in each point on this PDF for the Higgs, I have a different decay rate. So I can define the characteristic Higgs wave across all patches, right? This would be not the mean, because the mean is 0, but this would be the variance of this distribution, right? This green line here. I can define the average decay rate using this characteristic Higgs value, and then from the width of this distribution, I can also define the decay rate perturbation, right? So I can have the gamma bar, which is the average decay rate over all the universe, and the fluctuation of this decay rate or the perturbation of this decay rate from patch to patch. And then I go back to the Dvali et al. Paper, and I look at the perturbed evolution equations for the different components of the universe, right? So I have the evolution equation for delta phi and delta r for the perturbation in radiation, perturbation in matter. And eventually I have the perturbation for the gravitational potential and the Bardeen potential. So using the initial PDF for the Higgs field, I can now calculate the perturbation in the Bardeen potential. And so the perturbation, okay, before doing that, let me do a sanity check. Right, so we know that perturbation on superhorizon scales should freeze, right? Because, you know, as you exit the horizon, perturbations are frozen, as should be, for example, the Bardeen potential, the gravitational potential on superhorizon scales. However, when you have a non-adiabatic component of your fluid, that is not true, right? So when you have entropy modes can cause superhorizon fluctuations to actually evolve, and that's what we're doing here. So here, our entropy mode is the fact that the energy density of the universe is distributed differently between radiation and matter, right? Between inflaton and decay products in different parts of the universe. So this is actually an entropy mode. And we see that as long as the entropy modes are active, the Bardeen parameter changes. When the entropy modes die out, the Bardeen potential actually freezes. So essentially, this is sort of a sanity check to check the self-consistency of our calculations. If that was not, you know, if essentially the entropy and zeta dot were not matching, we would have done something wrong. Okay, so this is the money plot. This is actually our predictions or our calculations. So in the largest cosmological scales, what's called the Sachs-Wolf regime, delta T over T, so the fluctuations we see on the CMB, is actually trivially related to the Bardeen potential, right? To the zeta parameter, right? which I define here, right? In the delta n formalism, this is just delta n. So this has sort of different names. If we choose a sort of slicing of space-time, this can be equal to the gravitational potential or not. I don't want to go into details, but essentially this zeta is delta T over T as far as we care. So here we see a 3D plot where I have on one axis lambda is the self-coupling of the Higgs, right? The lambda 5/4. On this axis is the unperturbed decay rate of inflaton to fermions, right? Or the maximal decay rate, or the decay rate it would have for massless fermions. And here I have the Yukawa coupling. So red points, right, are combinations of parameters where the delta T over T from reheating is bigger than 10 to the 5. So these are immediately ruled out because we measure the sky is 10 to the minus 5. So if reheating alone gives me 10 to the minus 3, that's not the universe we live in. The green regions, right, the green dots have delta T over T less than 10 to the minus 5, so they are allowed. And the white region is actually 10 to the minus 5 or 10 to the minus 5, which means there, just from this analysis alone, we cannot really tell. So this is borderline, and it may be compatible, but give a feature that we can look for. Now, we need to just for the remainder of the analysis, I will commit to one value of the Higgs coupling, right? And I'll take 10 to the minus 2, so 0.01, which is sort of a reasonable assumption for what the Higgs does in the early universe. And I will look at a 2D slice. And here again, we see on the horizontal axis, I have the Yukawa coupling, right? The log. So 10 to the minus 1, 10 to the minus 2, for sort of heavy fermions. And on the vertical axis, I have the decay rate as a function of the inflaton mass. This black region, right, the hatchet region, is delta T over T less than 0.01%, so less than 1% of 10 to the minus 5, right? So this is below the sensitivity of Planck, right? Even if we see something here, we won't be able to detect it, right? As I said, the red region is ruled out. So this green region is actually an effect that is allowed, but with improved analysis, we may be able to see something. Right. Now, for gauge bosons, which is where I started, right, the talk, we cannot define. So if we have parametric resonance and preheating to gauge bosons, we cannot really define a decay rate, right? Because this is a non-perturbative process. However, we can do something very similar. We can simulate multiple patches, right? Each Hubble patch will have a different Higgs field, so we have a different gauge field mass. We evolve the gauge field in each patch and compute the inflaton and radiation energy densities. So if we have the rho phi and rho r, we have the delta rhos, which means from that we can also define the Bardeen potential. So immediately we see that, for example, if the Higgs PDF is such that in some Hubble patches, the mass of the gauge field leads to complete preheating, and in others to incomplete preheating, then the delta T over T will be 1, right? Because in one case, we will have instantaneous reheating, so very high reheat temperature. In other patches, we will have very low reheat temperature, so perturbative reheating, which means that delta T over T will be huge. It will not be 10 to the minus 5, will be 0.1 or 1. So we can immediately rule out a chunk of parameter space. But we can look at sort of this part where we have parametric resonance in the whole universe. And we take two sort of extreme values of G, right, of the gauge coupling. One that is too low for the standard model, one that is too high for the standard model. And so the standard model is somewhere in between. So for G.1, delta T over T is 10 to the minus 4. So it's already ruled out. So from this, we conclude that if the inflaton, or if the axion inflaton in this model decays solely to gauge bosons through parametric resonance, right? This is impossible if these are modulated by the Higgs. You can still decay to photons, but you cannot decay to standard model to gauge bosons. Now, if you decay to both, right? If you allow decay channels to both photons, so massless and massive gauge bosons, then it becomes a numbers game, right? Because the photon part will not care about the Higgs. The W and Z part will do care about the Higgs. So the decay ratio of the ratio of the coupling of the inflaton to massless and massive gauge bosons will give us sort of a different contribution of the two decay rates to the reheat temperature, which means it can be ruled out or still compatible. But it's a numbers game that we didn't pursue because it's one more parameter to put into the analysis. But it can be done with an analysis or trivial. Okay, let me take one step back. How much time do I have, by the way? Like 10 minutes or so?
15 minutes, yeah.
15 minutes, okay, more than enough. Okay, so the predictions of inflation, right? It was a scale invariant spectrum, and I just showed how Higgs reheating can actually completely mess up sort of the amplitude of the fluctuations, right? Allowing us to put constraints on both the couplings of the inflaton to standard model fermions, as well as the self-coupling of the Higgs at large energies. But also regular inflation, let's say sort of the vanilla model of inflation, predict Gaussian perturbations, right? And as of today, there's no evidence of non-Gaussianity in the sky, right? So the Planck has put severe constraints on primordial non-Gaussianity, right? So as far as we can tell, the signal is largely Gaussian. So how does the modulated reheating through the Higgs deal or affect Gaussianity or non-Gaussianity of the CMB? So we can do exactly the same, we can actually now go and do a slightly more sophisticated method that I described before. So again, we start with a ensemble of patches at the end of the universe with different Higgs values, but instead of looking at the decay rate and its fluctuation, we actually do a slightly more involved analysis where at each patch we look at rho phi and rho r, right? Again, the energy density in inflaton and radiation. And through that, we can actually calculate an ensemble of gravitational potentials and Bardeen potentials, right? So we can actually do an ensemble of Bardeen potentials, which means an ensemble of delta T over T's, right? We can see what is the ensemble of temperature fluctuations at the end of inflation. And here I show for one realization how does the PDF of Z of the zeta, the Bardeen potential, or the delta T over T evolve with time. This is, I think, 1 evolves after inflation, 2 evolves after inflation, 5 evolves after inflation, and the green one is where it saturates. The first thing we see, right, is that this is pretty non-Gaussian, right? I mean, this, if you look at this probability distribution, you will not immediately say, oh, this looks like a Gaussian. No, it doesn't. It has a tail here and it has a peak on the other side. So clearly this will induce primordial non-Gaussianity. Now we can define the local non-Gaussianity FNL, right? If we take we can define it in this way, right? The G is our distribution, right? In this case, the distribution of temperatures. And it has a Gaussian part, and the non-Gaussian part can be defined in this way. Now we can compute the non-Gaussianity having this distribution by looking at the skewness. The skewness is the third moment of the distribution. And actually this FNL is nothing more than the skewness divided by the RMS value, right? So technically it's the skewness divided by 6 times the 4th power of the temperature, the RMS value of the temperature. So we have everything, right? The assumption we make is that the average temperature, so this 10 to the minus 5, is dominated by not by modulated reheating, but by sort of CMB fluctuations, by inflation fluctuations, and the skewness or the non-Gaussianity is dominated by modulated reheating. And here are our results. FNL5 is where the Planck bounds are at the moment, so between -5 and 5.1. So you can see that on the same plot, right, the non-Gaussianity already gives a tighter constraint by about an order of magnitude in Yukawa couplings and gamma naught, right? So this white line was where the constraints were before with the analysis of just delta T over T, the magnitude. Non-Gaussianity allows us to go 1 order of magnitude deeper into the region. So we tighten constraints using non-Gaussianity. Sorry. And now allow me to say that I have just looked at the large. I mean, I did not look at all the analysis that I did has no scale information. Right. I just assumed that I look at the largest possible scales on the sky. So I do not look at how the Higgs fluctuations will depend. They will be red, right? Because as inflation goes, scales that enter the horizon later will feel a slightly different Higgs, and so slightly different Hubble, and so on. Okay, so I will come to that in a minute. So before I go towards concluding, let me say that there are 2 possible origins of non-Gaussianity, right? The initial Higgs PDF is completely non-Gaussian, right? Because the Starobinsky PDF is exponential of -h to the 4th, right? So the initial PDF is not Gaussian. And also the relation between the Higgs value and the decay rate is nonlinear. I mean, this is a completely nonlinear. It's the 3/2 power of 1 minus h. So the question is, what is the main source of non-Gaussianity? Is it the non-Gaussianity of the Higgs PDF? So if I change the PDF by a bit, it gives me a completely different result. Or is it the inherent phase space, sort of phase space modulation due to kinematics? So actually, we checked that by using a Gaussian PDF for the Higgs field with the same variance as the Starobinsky PDF. And the results, so the 2 lines, the 2 pairs of lines are actually the Starobinsky PDF and the Gaussian PDF. So we see that the shape of the initial Higgs PDF is not the dominant factor, right? So by changing the Starobinsky PDF by a bit, keeping the same variance, the non-Gaussianity result will be exactly the same. And you see, to within an order 1 factor. However, this is the important factor. The fact that the correlation or the dependence of the decay rate on the Higgs value is nonlinear, it will give non-Gaussianity. That's why in the original papers, right, if we take gamma to be just proportional to the spectator field, you don't see that. You don't see non-Gaussianity. Okay, now let me say some caveats about our analysis. And actually, the caveats in our case do not make our results worse. They make it better. So first of all, relaxing the de Sitter approximation, it has been shown that it can increase the spectator field amplitude. This was done by Hardwick et al. Based on the stochastic inflation formalism. And it shows that it can actually increase the fluctuations beyond the Sarbinsky result. Also, the Higgs is not 1 degree of freedom, it's 4 degrees of freedom, right? So essentially, it's a doublet, it's a complex doublet. So what we should have used is a 4D random walk, not a 1D random walk. And a 4D random walk is actually gives you a larger variance than a 1D random walk. This was done by Yates et al. in 2020. And it also shows that we could have used a larger variance for the Higgs. So our results are stronger than what we presented. And for the non-Gaussianity, we only use the FNL, right? We only use the skewness. However, we have the full distribution. So we have the full power of going to tau and L and so on, right? Using higher order correlators. And there was a paper by Chen et al. in 2018, which showed how we can use higher order correlators of FNL to look at CMB data and put constraints. And this is also something we have the power to do. And finally, we used lambda equals 0.01, right? We did not push to some fine-tuned, or some model building might say, okay, but lambda can be 10 to the minus 3, 10 to the minus 4 during inflation. We were very conservative in some sense with our lambda. So all of these things can actually say that our results can be stricter rather than looser. Okay, so conclusions: the Higgs as a light spectator field during inflation will cause reheating to standard model particles to be space dependent. This space dependence will result in Higgs reheating induced fluctuations of the temperature and also significant non-Gaussianity. By comparing with Planck observation and with future observations, we can constrain the standard model parameter space. And of course, the bounds are tighter for reheating to heavier particles, larger Yukawas, right? And the non-Gaussianity is tighter by 1 order of magnitude just by FNL alone. And one thing we can exclude is we can exclude reheating, preheating to standard model Higgs gauge bosons. So the inflaton cannot decay to W and Z bosons parametrically because that would create too large delta T over T. So this is a general phenomenon in a sense, right? The effect of the Higgs during reheating is a general phenomenon, a general sort of effect that is there, which means that it can have more phenomenological consequences in a sense. For example, we can add spatial information for delta T over T and FNL, which will increase our constraining power. We can accurately compute the stochastic evolution of the Higgs, which we didn't do. We just used the Sarbinsky PDF. And also any effect that takes place during reheating, for example, leptogenesis or baryogenesis that happens during reheating will also be affected by this, right? Because in inflationary or reheating leptogenesis, the standard model particles will have different Higgs masses, which means that you can have slightly different baryon numbers in different parts of the universe, which will lead into cosmic infrared background fluctuations. So there's a way to probe the Higgs potential during inflation and during reheating by looking at what happens at those very high energies. And more importantly, the self-coupling of the Higgs during inflation is not just a number, right? It's a number that tells us how the standard model flows through a normalization group from today or from sort of T, V, LHC type energies all the way to the inflationary energies. So this actually gives us a chance to see or to probe or to constrain the RG flow of the standard model all the way from here to inflation. And of course, I mean, I just to say that this is just one of the standard model or the SM or BSM physics that we can study during reheating, right? If the inflaton, if the Higgs is the inflaton in the Bezrukov and Shaposhnikov idea, then we can see how exactly how Higgs preheating occurs and what sort of temperatures we have. We can have magnetogenesis. So if we couple the standard model photon to the inflaton, we can actually get intergalactic magnetic fields. We can get gravitational leptogenesis, which allows us to put constraints on the mass and the nature of heavy right-handed neutrinos. Or we can have, for example, axion inflation leptogenesis, which also allows us to put some constraints on the mass of heavy Majorana right-handed neutrinos. And this is essentially all I had to say. I mean, I have more things to say, but I will not go into more details about other projects. I will leave it to here.
Thank you very much. Do we have any questions?
Hello, thanks for a nice talk. Can I ask one question?
Of course, of course.
Okay, so you mentioned you want to look at a Higgs, and so the standard model Higgs, obviously we know lambda at a low scale from the mass measurement.
Yes.
If you assume the minimal model, so you assume lambda equals 0.01. So to what scale of reheating scale does it correspond to?
Well, thank you. Well, actually, you know, if you actually take the standard model and the mid value of the top quark, and you start flowing it up, then at some point you become negative, right?
Yes. So, yeah, exactly. It's unstable or metastable.
So I did not consider that. I said what we did was we assumed that there is some way of some extra BSM physics, some extra particle species that will stabilize the Higgs potential, right? But what we want to do, and what we're discussing with the other people in the collaboration, is actually do the RG flows and say, okay, exactly what you asked. What sort of top quark value and reheating scale can I take that will allow me to put, that will allow the Higgs to not turn negative and still get sort of observationally relevant reheating results. So until now, I mean, I did take the standard model Higgs, but I was liberal with lambda because I did not want to deal with Higgs potential instabilities and so on.
Okay. I guess it would be interesting to look at that and to also take into account that you actually always have both decays to tops and to gauge bosons in photons.
Exactly. No,
technically fixed.
Right. So this was actually right. So here we did sort of the proof of principle, right? We say, okay, let me say I decay only to one. I mean, even all the plots I showed you, because I only had one Yukawa, right? I said, okay, I decay to one family, but essentially, as you said, you're completely right. The full thing would be, let's take everything, right? Let's take decaying to both top quarks and to gauge bosons and see how the interplay of these two changes with the parameter with lambda and the different couplings. I mean, this makes it a higher dimensional parameter space. Of course, but this is something that is within our power to do, and we actually want to do it. Yes, we just haven't done it yet.
Okay, sounds interesting. Yeah, thanks a lot.
And also, for example, a caveat would be in extension of the standard model where the Higgs is a composite particle, right? So if during inflation the Higgs has dissolved into its constituents, the analysis changes completely. Of course, these constituents might actually get de Sitter fluctuations during inflation, but that is a different that might actually wash out completely the effect, right? So again, we took sort of vanilla assumptions, but any other BSM assumption you have can be recast into this language and calculated.
Okay, now I think it would be interesting to see what's happening actually in the standard model or minimally
Right.
If you minimally extend it when you want to solve the stability problem.
That is something that's actually ongoing. We are thinking about sort of taking the how do you call it, the error bars in the top quark mass and doing the RG flow and seeing exactly what happens and what top quark mass we need to assume and what inflationary scale we can get away with, in a sense.
Okay, now I'm looking forward to that. That sounds interesting. Thanks.
Any other questions? So you mentioned the contribution to the CMB temperature fluctuations. Would you also expect an additional contribution to the e-polarization of the CMB?
To the e-polarization? That's a good question. I don't think so, right? Because the only thing that it does, is it actually changes really the temperature only, right? So in each Hubble patch, you get a different temperature fluctuation. I don't think that the polarization will be affected.
I mean, it does give you extra fluctuations on the last scattering surface, right?
Right.
So I don't know. It might give an extra contribution to polarization as well, because it also adds to the quadrupole moment. I mean, it's
right.
It's relatively similar, I guess, to just generally increasing the amplitude of primordial perturbations, of scalar perturbations.
Right. Yes, but in a sense, something that's important is that these are uncorrelated. So essentially, you have two uncorrelated sources of fluctuations.
Yes.
So essentially, even if it does give an e-polarization addition, it would be interesting to see that this is something that is sort of decoherent in a sense with what we have on the CMB. That actually, if that exists, that would be interesting. And actually, something that's interesting to me would be also somehow my cursor is not. So go into this white region and see if something can be done there, right? Because then you actually have two of them that are competing, and then we might actually get a non-trivial signal. Or if we get something that is also, I mean, then I go into the model building weeds a bit, but I find it interesting. If there's a shape dependence, right? Well, I mean, let's say during inflation, the Higgs becomes tachyonic for some range of EFOs during inflation, and then it becomes stabilized. That means that I can get a very large sort of peak of Higgs values at a specific scale, right? And be suppressed or much lower through the other inflationary history, and then it might be more, or it will be easier. It could be easier to get a feature on the CMB to look for sort of template. So even if they are lower, if they have strong spatial dependence, they may be easier to pick up. And could that be interesting, for example, for the low Ls? I mean, if that scale happens to be the low L scale, you know, could that have some interesting interplay? You know, if you take comparable or big enough delta T over T for the Higgs and from the inflaton, does it help or does it make even worse the low L anomaly, for example?
I would expect it to make it worse because
right, exactly, because you will get more power.
We observe less power than we expect in regular lambda CDM. Right. Yeah.
But then is the question, you know, can you make it anti-correlated with? I mean, here they are uncorrelated. Lowest order they're uncorrelated, but can you make it anti-correlated with inflationary fluctuations such that you reduce the power? Again, too much model building that I would, you know, that I would hope to need to do in a sense.
Mm-hmm.
I mean, if the Higgs talks to the inflaton directly, then, you know, this is not out of the reach in a sense, or out of the question.
Yep. Interesting. Do we have any more questions? No? Okay. Thank you again, Evangelos.